What you see here is gallium indium tin, a eutectic alloy that is liquid at room temperature. We use it to model the process of continuous steel casting. And to get a better insight into the flow structure, we use contactless inductive flow tomography. Contactless inductive flow tomography, or SIFT for short, is a measurement technique that relies on basic principles of magnetohydrodynamics. In other words, if a conductive fluid, in our case gallium indium tin, is flowing through an externally applied magnetic field, the flow of liquid metal will perturb the magnetic field. And these perturbations we can measure outside of the fluid domain, and from these measurements we can calculate and reconstruct the velocity field.
Hi, my name is Ivan Glavinić and welcome to the MHD laboratory located at Helmholtz-Zentrum Dresden-Rosendorf. Behind me is mini-limcast, a laboratory experiment that we use to model the process of continuous casting. But before I go into more detail, I would briefly like to explain the process of continuous casting.
More than 95% of steel produced in the entire world is produced by continuous casting. Batches of liquid steel are brought in ladles and poured into the tundish, which acts as a buffer storage. From the tundish, the liquid steel flows through the submerged entry nozzle and into the water-cooled mold, where it solidifies. Flow conditions in the mold are important for the end quality of the product. And that's why we investigate the process, develop measurement techniques and control strategies here in our laboratory. Mini-limcast circulates liquid metal in a loop. Metal is stored in the storage tank. From there it is pumped to the tundish on top. From the tundish, the liquid metal flows through the submerged entry nozzle and into the mold. Liquid metal leaves the mold at the bottom and flows back to the storage tank. And the flow rate in the system is regulated by the position of the stop rod at the inlet of the submerged entry nozzle. To influence the flow in the mold, we have an electromagnetic brake, which at its highest settings generates a magnetic field strength of 400 milliteslas with an electric current of 600 amps. And finally, to measure the flow conditions in the mold, we use contactless inductive flow tomography. Two excitation coils generate a vertical magnetic field of 1.5 milliteslas in vertical direction, and to measure the magnetic field generated by the flow, we use 14 gradiometric coils, 7 on each narrow side of the mold. Flow-induced magnetic field is incredibly small. It is about 50 to 100 nanoteslas. That's roughly 1,000 times smaller than the magnetic field of the Earth, and more than 1,000,000 times smaller than the magnetic field that can be generated by the electromagnetic brake. We use high-precision AD converter to digitalize the signal and extract the flow-induced magnetic field. Then we use that information as an input to the linear inverse problem to reconstruct the velocities of the liquid metal. The key information about the flow structures such as jet impingement point and the oscillations of the jet are forwarded to the controller, which then decides on the required set points for the current through the electromagnetic brake to achieve a desired result. At that point, we find ourselves in an interesting situation. When we change the magnetic field of the electromagnetic brake, the magnetization vector of its ferromagnetic parts also changes. And since our SIFT excitation magnetic field partially goes through this ferromagnetic domain, it is also distorted, resulting in a high change of measurement value. Observe what happens when we change the current to 200 amperes. The value that we measure is now 1,000 times higher than what we expect. The reason for this is the magnetic hysteresis exhibited by the ferromagnetic parts. But we can compensate for this by creating a numerical model used for compensation. As you can see here, it's compensated quite well. Now we can try the same thing while the liquid metal is flowing. You can see the live reconstruction, and if I change the current through the EMBR, we are still able to do the reconstruction of the flow. One additional tomographic technique that we use is called mutual inductance tomography, which can detect the gas-liquid ratio in submerged entry nozzle. The sensor here has 8 coils, where each coil can function as a sending or a receiving coil. And based on the air-liquid distribution in the submerged entry nozzle, we get different signals on each coil pair. We can do this since gas, in our case argon, and liquid metal have drastically different electrical properties.
This video was and is a short demonstration of our experiment, measurement techniques, and some of the challenges that we are facing. We set our goals here to demonstrate the feasibility of utilizing tomographic measurement techniques in an industrial process control. a field that's just emerging, partially due to the complexities of the real-time reconstruction and partially due to the constant need for new information and process improvement. In total, we are a team of 15 young researchers and numerous industrial partners, advisors and supervisors that are currently researching this topic. With that, there are 3 additional demonstrations within this project with the same end goal, but with a focus on a different industrial process. I urge you to take a look at their presentations and follow us in the future for more detailed dissemination of results.